The data from NHANES are not being updated.
Are not being
Updated. The updated the ranks there because it's about it's from June 2016.
Yeah, no, those are it's the same data set that we use for the second edition of the book. So
Yeah.
yeah, there's plenty of newer versions of NHANES out there, but they all follow the same basic sample designs.
Yeah. And just do that.
The charger.
Oh, the charger.
Okay, good morning, everyone. We'll get started in another couple minutes or so here, just give people a chance to arrive and log in on Zoom. So. Morning. Okay, good morning, everyone. Happy Friday. So it's lab day. So I hope everybody has their fingers ready to follow along here and ready to start programming a little bit. So today, the primary focus is going to be on conducting variance estimation using the NHANES data. And we're going to walk through how to do that in both Stata and R. So again, you're very much encouraged to follow along as we're going through these examples, and of course to ask questions if you have concerns or questions about any of the code that we're using as it might pertain to your own data sets. Okay, so again, everybody's very much encouraged to follow along. What I have up on the screen are the lab notes for today. This is laboratory session 2, which you'll find in the computer lab notes folder up on Canvas. So right here, you see among the 6 file folders on Canvas, the first one's called computer lab notes. And that's where you're going to see laboratory session 2, 2024. So that's the document that I have open right now. So this lab session, we're going to look at examples of computing means. We're going to also look at examples of computing tables of estimates. And in all of these cases, we're going to talk about how to compute variances of those estimates. And we're also going to look at computing estimates for different subpopulations. So we'll make use of survey by and R, for example, use of subpop within Stata. And I'll reiterate those points about the importance of doing this unconditionally when we're using linearization for variance estimation. Okay, so we're going to look at a variety of different commands in both Stata and R. And those are kind of always going to be summarized on this first page of the computer lab notes, like what commands we're going to be explicitly focusing on a given day. And most of these examples, you can find additional examples of the same type, same flavor in chapters 5 and 6 of applied survey data analysis. Okay, so you're always going to see what commands we're using, what chapters you can find more information in, and then specifically what we're going to be focusing on today. Okay, so probably the easiest for following along, depending on whether you'd like to focus on Stata or R, or if you're using both, that's fine too. What I would recommend is highlighting the entire block of code that you have for Stata or R. Once you have that highlighted, here, for example, I've highlighted all the Stata code starting on page 2. I would encourage you to copy that Stata code into a do file editor within Stata, if you have Stata open. Okay, so within the Stata software, you can go into Window and do file editor and say new if you don't have one open yet. I already have this do file editor open, so I see that as an option. But you can start a new do file, and then in that blank do file window, just copy and paste that entire block of Stata code that's in the computer lab notes. Okay. Now, of course, when you're doing your own analyses, you'll be writing this code from scratch, but we're going to walk through each of these commands, what they're doing, so that you can then modify them for your own data as you start to do your own analyses. Okay. Now, same thing within R. I'm working within R Studio. So if you're working within R Studio, you can actually copy and paste the code into this script window that's part of the R Studio default here. And you'll see kind of as we run the code piece by piece interactively, you'll see the results pop up in the R console that you see in the lower left. But I'd encourage you to copy that code into the R script window, and then we're going to run that line by line as we go here. Okay. And then we'll talk about some of the other features of R Studio as we go. All right, so I have copied both of those blocks of code, the R code. Remember, don't copy the Stata code into the R code window and vice versa. That's going to cause all kinds of headaches. So make sure you're copying the R code starting on page 3 into R, and the Stata code starting on page 2 into Stata. Okay, so let's make sure to do that. But we're going to walk through this code now within each of the software packages to see how exactly to get this going. Okay, I think that's big enough. Hopefully everybody can see that. Is that font big enough? Everybody can see on the screen? Is it okay? Need to be a little bit bigger? Yay, nay, a little bit bigger? How is that looking? Is that okay? Everybody okay? Okay. All right. So let's start within Stata then. So this is the Stata code again that's in your second lab notes document. First things first, I'm setting a working directory. Okay, you don't have to do this, but this is the easiest way to operate, especially when you're reading in data. Okay, so in Stata, I'm setting a working directory with that CD command, stands for change directory. Now, on this machine up at the top of the room, I'm pointing to a directory on the ISR network where I have the data sets saved. Okay, for you to open the data, you will need to point to the directory on your own machine where you have downloaded the NHANES data set from Canvas. Okay, so if you haven't yet downloaded the NHANES data set from Canvas, you're going to go into data sets. And you're going to go to this file that says NHANES 1112. It's at the bottom of the list of data sets. You're going to download that Stata format data file somewhere on your machine that's easy for you to access. Okay. Okay. The The deeper that you save that file, the more directory name you're gonna have to type when you set the directory. Okay, so save it somewhere where it's easy to specify that directory. Okay, I go through that process in Stata. I save that data file in this particular location. It's going to differ depending on where you save your data file. Okay, so once you've done that, make sure to set your working directory to that location using that first CD command. So you're going to have to update that for your own work. Okay. After that point, the log file that we start opening the data, all we have to do is type the names of those files. We don't have to type the directory every single time. Okay. So once I've set that working directory, this second line here, and this is just good practice in Stata, this is going to create a working log file where all of our commands and all of our output will be saved from the Stata session. Okay. Even if you make errors, that's okay. Those errors are going to be saved in that output log file. Okay. So this will give us a written history of everything we've done, including any output that we've generated that we can refer back to at a later point in time. Okay. If you don't want to create a log file, that's fine as well. You can just copy and paste interactively out of the Stata window, but I like to have this working history anytime I have a Stata session so I can go back and see what I did. If I forget to copy and paste something or something like that, I know that that's always being appended in the background whenever I run something. Okay, so that's what that log using command is doing. And the replace just means if that file already exists in that directory, just replace it with the one that we're creating here. Okay. Okay.
Select save as.
Say again.
Select save as.
Not exactly. It's just it's creating a new file. That's all. It's initiating a file to which your output will be appended. And if that file already exists, it's just overwriting what was there to begin with. So we're starting from scratch with that file. Yep. Okay. Then the use command in Stata opens the data file and puts it into Stata's working memory, the data file that we wish to work with. And again, because I've already set the directory, all I have to do is type the name of that data file, exactly as it is as you saved it. Okay. So I go ahead and run that line, and in the do file window, to run one of these lines, all you have to do is highlight the lines that you want to run, and then click on this little button on the toolbar that says execute selection. It looks like a piece of paper with a play button on it. That will execute the lines of code that you've highlighted in the do file editor. Not everything, just the lines of code that you've highlighted. Okay. So if I run those 3 lines of code by clicking on that button, I can go back to my Stata results window. I already had that log file open, but I've opened that data file, okay, and I'm ready to go with the subsequent analyses that I've started. My log file was already open to begin with. Okay. All right, everybody with me so far? Any issues or questions? I want to make sure everybody has the data file open. I can tell I have the data file open in Stata because I see the variables window populated. Okay, that shows me I can, whatever variable I want to work with in that data file, I now have access to all those variables. Okay, so is everybody with me? Got the file open? Any issues? Yep, Jones. Oh, you're good. Okay. Questions?
I have a question.
Yep, Israel.
It's giving me an error, just unable to change it to.
So it has to be an actual directory on your machine. Yeah. So if that's a directory on your machine to which you have access, you should be able to change that directory. If it's a restricted directory that you don't have access to, you can't. That's what would give you that error. So either that directory doesn't exist or you don't have access to it. That's what would cause that message.
Maybe I opened the data outside.
You can also, so if you're having a problem with the directory, you can go to File, Open, and then just find where you saved the data file and just open it that way. That's another way to do it. It's just good to practice with using the actual syntax for all these steps. Okay.
And if from that, you must get the link. If you click open, it will give you the link.
Right. Right. It's just better to have the syntax saved. Okay. Next step, and this is key so that everybody's on the same page. we're renaming all the variables to be in lowercase. So this is a nice data management command within Stata. If you have a data set like what we see here, where you have a mix of some variables in lowercase, some variables in caps, because Stata is case sensitive, this rename command converts everything to lowercase. So we're saying rename every single variable, that's the asterisk, to lowercase. Then we can just type lowercase for all of our subsequent commands. Again, this is an option. You don't have to do it, but it's helpful for data management purposes. So you can see when I did that, all of the variable names are changed to lowercase. Okay, okay. Optional, but helpful. Okay, then this DES command is just giving you a basic descriptive summary of what you have in the data set. And optional, not required, but good as a starting point to get an understanding of what data set you have open. So if I go into the results window here within Stata, for each of the variables in the data set, I'm going to see how many observations I have, how many variables are in total, and then for each of the variables, I see their types and their labels. Okay, so I have a good idea of what variables I have available to work with here within the data set. And you can see within NHANES already, here's the block of variables that corresponds to our design features. So we have the interview weight, we have the medical examination weight, and then we have those sampling error codes that we would use for variance estimation using linearization, right? The PSU code and the stratum code that we would input for linearization. What you do not see are replicate weights, okay? So the NHANES data producers chose to provide sampling error codes that enable linearization. If you wanted to do replication, you'd have to create those replicate weights on your own, on the fly. We're going to see how to do that. Okay. Okay, so it's always, again, just to familiarize yourself with the data set, good idea to look at some of this basic descriptive information. Okay, everybody with me? Comments, questions? Definitely stop me if any issues come up. Okay, once you have the data set open, good to look at some basic descriptive statistics before you jump into the actual design-based analysis. Okay, so for example, if I want to look at a frequency distribution on age, I could just use the simple tab command. This is not giving me any kind of population estimates, okay? This is just to describe the variables that you have in the data set and see what kind of values you're looking at. So what this is saying is tabulate the values on the age variable as they are and include as part of that tabulation missing values. Okay, so you can see what percentage of the data set or what percentage of the values on that variable are missing. All right, that's what that missing option is after the comma. So if I run this one line in my Stata results window, I'm going to see this frequency table for all those different possible values of age. So you can see there's plenty of people who are under the age 18 in the NHANES data set. But in addition, I'm going to see any missing values. I see 100% of the values on the age variable are valid. I don't see any missing data. So that's a good thing. I don't have any missing data problems on this particular variable. The variable is 100% populated. So on your homework, this is an example of a variable that has complete data for everybody in the data set. You could use this variable to compare complete cases with incomplete cases on your variables of interest, okay, for your data set. This is what's meant by a variable with complete data on everybody. There are no missing values. So I could compare complete cases with incomplete cases in terms of the mean age or something like that, and see if there's any bias introduced by analyzing the complete cases only. Okay. Okay. So you could do that for other variables. I'm just demonstrating this for age right now. You could look at frequency tables for other variables. Always a good idea to do that with your variables of interest before you dive into the actual analysis. Yep, question?
Explain it again, the age variable.
So the homework is asking you for all your variables of interest, right? Suppose you have 10 variables that you want to analyze in your data set. For all the variables of interest that you want to work with, create an indicator. Okay. This case either has complete data on all the variables of interest, they get a 1, or this case has missing values on some of the variables, they get a 0. And then you're going to be comparing the 1 and 0 groups in terms of distributions on variables like age in this example, because age is complete for everybody. Make sense? Other questions so far? Okay, so that gives us a chance just to look at, again, this is not a population estimate. This is just telling you what you have in your current data set. Okay, given that age information, then the next block of code here is recoding age into categories. So if we wanted to take a continuous variable and group it into categories, this is one set of code that you could use for that task. There's different ways to do this in Stata. This is one possible way to do this. Now, very important if you're a Stata user, because I'd say this is the #1 mistake, period, that Stata users make when they manage their data. Okay, Stata treats missing values as the largest possible value in the data set. Okay, so if the largest actual value on a variable of interest is, say, 99, and you have a condition that says if age is greater than or equal to 95, okay, Stata will include a missing value as satisfying that condition. Okay, very, very critical. So when you're creating groups, say in this example, I want to create age category 3. If age actually had a missing value on it, we don't have that in this case, but if age actually had a missing value on it, and I wrote a condition like this, right? I just moved that second piece of the condition out of parentheses. Bless you. Any missing values on age would be recoded to category 3. It is fundamentally important, if you're a Stata user, that you do not make this mistake, especially for variables that have a large proportion of missing values. Otherwise, you're effectively imputing a value of 3 for every single case that has a missing value on that variable, which could lead to highly incorrect conclusions. Okay? I can't emphasize this enough. Everything we're talking about in this class doesn't matter if you're not careful with the data management. Okay? So that's why it's always important to look at missing values on your variables. And when you're thinking about recoding them into categories, be very, very careful with how you handle missing data. Okay, because again, doesn't matter what I'm saying about weights and variance estimation and everything else. If group 3 is fiction, all your analyses are going to be fiction. Okay, very important.
So in this case, the missing value should be recorded.
What should happen in this case is the way I had the condition initially in there. What this is saying is replace values on that new variable age cat 3 as being equal to 3 if age is greater than or equal to 51 and age is less than a missing value. So if age is missing, it would be excluded from that calculation. Remember, Stata is treating a dot, a system missing value, as the largest possible value in the data set. Okay. Now, I don't have to worry about that because of age in this case, but the general message it pertains to every other variable you're looking at when you do this kind of recoding.
And if you said that it's different from point for missing.
You could say not equal, but Stata also codes like a dot A, a dot B, a dot C, a dot D for different types of missing values. And those would then be included as well. Okay. So the easiest way to go about this is to look at that frequency table, understand what the missing values are, and make sure they're not included in this recoding. Yep. Less than in this case is fine if the only missing value that you see in the data set is a dot.
Yeah.
Yep. Okay, so what this is saying in total, we're generating a new variable called age cat 3 as being equal to 0. then we're replacing the values on that variable with either a 1, a 2, or a 3, depending on which condition is satisfied. Okay? And Stata doesn't want you to write and, it wants you to write the ampersand. That's what that symbol is. Okay? That means and. So age has to be greater than or equal to 0, and age has to be less or equal to 17 for that condition to hold. Okay? So we have to actually use that ampersand symbol. Then, once we have this new variable from running this block, always a good idea to look at a simple frequency table for that new variable, again, including missing values, to make sure that everything's consistent in the way those missing values are being handled. All right, so I shouldn't see any zeros on this variable. I shouldn't see any missing values if everything went according to plan. Okay, so I'll run this block of 5 lines at once using this when I hit that play button. Then I take a look at my results window. Sure enough, I have all 9,756 cases accounted for, and they've been recoded into one of these 3 categories. Now I can use that age cat 3 variable for subsequent analyses, whatever I want to do with it. Okay, but be very careful about missing data. That's the message here. Okay. Okay. Now, suppose we're happy with the data management and we're ready to go with the actual design-based analyses. So we want to get into the computation of population estimates, the variance estimates that we've been talking about, and so forth. We're happy with the data set that's been created. Okay. Okay, first things first in Stata, we're going to globally set these design variables. We've taken the time, maybe it's a half an hour, maybe it's an hour, maybe it's half a day, to review the documentation. We're confident that we know exactly what those design variables are going into the analysis. We've read those sections. We know what variables we should be using for variance estimation. Okay. We globally declare those design variables using the survey set command. First variable listed, if we're using linearization, is the name of that variable containing the cluster codes. In the case of NHANES, this is SDMVPSU. Okay. After that cluster code variable is listed first, then we put our survey weight variable as a p weight in square brackets. So the probability weight variable we're going to use in this case is WT-MEC 2 year. Then after a comma, we indicate the variable containing the stratum codes for sampling error estimation as the strata argument. Okay, so strata with an A, then in parentheses, the name of that variable containing the stratum codes in our data set. Okay, and Stata, unlike R, will assume that the cluster codes are nested within the strata codes for variance estimation. Okay. Okay, so let's go ahead and run that one line and take a look at the Stata output when we run that. Once you set those design variables, you make this kind of global declaration. Stata is just going to echo what you've defined for subsequent analysis. So our sampling weights, they're in the WT-MEC 2 year variable. Our variance estimation technique by default, linearization. Okay, remember that's always going to be the default here. Single unit, what does that mean? Okay, single unit says if Stata identifies a stratum that only has one cluster code present, no standard errors for you. Okay, I am a big fan of that being the default in Stata. Okay, another very common question people have is, I think I've done everything right. I set my design variables, I found the right variables, I set everything up, but Stata is not computing standard errors for me. Is Stata broken? Okay. My follow-up question is, did you delete any cases from your data set? And the answer almost 99% of the time is yes. Okay. Cases were thrown out of that data set by the person doing the analysis that they didn't care about. Again, the subpopulation issue. And that deletion process resulted in the deletion of an entire sampling error cluster code. It just so happened that that sampling error cluster code was one of 2 in one of the strata. And so Stata is identifying and saying, you want me to do linearization. But remember, I can't do linearization because we're dividing by a sub h minus 1, the variance estimates. Okay. So what Stata does, it says, if I see that problem, you're not getting a standard error because it's undefined. That's what single unit missing means. It's saying there's a stratum with only one cluster, and so you're not going to get a standard error. Okay? So the data producer should give you at least 2 clusters per stratum if they want you to use linearization. Okay? But the data user can actually invoke that problem by deleting cases they don't care about. Okay? This is the distinction. All right, there are other options for single unit that we'll eventually get to, but for now, that's what that default means. Okay. Then Stata just echoes the stratum codes and the cluster codes of variance estimation, and the finite population correction is assumed to be 1. Okay, so we're essentially ignoring the FBC in this case. All right. Questions about setting those design variables? Although this is 1 line of code, this should take you an hour or 2. Why does it take an hour or 2? Because you need to read the documentation. Okay, everybody clear on that point? Again, something else I can't emphasize enough. Sarah, did you have a question?
I do. So if I was using a data set that instead had replica weights and SAS and subdomains, is there an instance where I could get a similar effect where by deleting or by only choosing things or only choosing a subsample, I'd end up with errors in my standard error, or no?
No. Remember, so a key point here is that this only applies to linearization.
Okay.
All this single unit business, variance estimation, only applies to linearization. All the sub-pop stuff, only linearization. With replication techniques, the input for the variance estimation, just the point estimates from the replicate samples. That's all we need. Okay, so you're going to get the same answer whether you delete or whether you don't delete. Best practice, don't get into the habit of deleting cases. Even if you're using the jackknife, still turn on the sub-pop options. Still read in the entire data set. Okay, best to get into that kind of habit when working on these kinds of analyses. But you'll be okay if you make that mistake if you're using a replication technique. Okay.
Okay.
Just get into the habit of creating these indicator variables for your sub-pops and not deleting cases that you don't care about. Okay. Other questions about the survey set here? Other questions? Okay. Next command in Stata is survey describe. This is a very cool command within Stata because it gives you descriptive information about the complex sample design features that you've just declared globally. So survey set should always be paired with survey describe. Okay? So I'm just going to run survey describe by itself. And what that gives you is this nice summary table that shows you all of the strata defined by the sampling error calculation model. So in this case, there are 14 strata for the NHANES data set. Okay? Maybe they were collapsed, maybe they were combined. This is what we've been provided in the full data set. Okay? And then for each of those strata, how many sampling error cluster codes are provided for that strata? So again, pop quiz here. Can we use balanced repeated replication given this sampling error calculation model? George, you say yes. Why yes? Jupiter, you say no. Let's have a debate. Who's with Jupiter? We can't use this data set. We can't use this data set for BRR. How many people vote for we cannot? Let's see, 1, 2, 3, 4. How many people vote for we can? How many people didn't raise their hands? Right? Why can we not use this data set for balanced repeated replication?
Yes,
Exactly. Some of the strata have 3 clusters present. Remember, for balanced repeated replication, every stratum has to have 2 cluster codes. Okay. So looking at this table says, well, We could use the jackknife
maximum or at least.
to exactly. It's a half sample technique. We're deleting one of the two clusters in every stratum. So we could use the jackknife, we could use the bootstrap, but we can't use BRR. Okay. Also, you see the total number of respondents in each of the different strata, okay? As well as the average number of respondents per cluster in this case. So this 314.7 says that on average, there's 314 respondents per cluster, okay? So remember that design effect formula that Kish derived, not the ratio of variances, but 1 plus B minus 1 times rho, that's our B. So in that design effect formula, our variances are going to be inflated by a factor of 1 plus 313 times whatever that rho value is for a given variable. So that rho value is 0.05, massive design effect, right? That's the clustering effect. NHANES, 14 strata, 31 clusters. This is what they've provided you with. That's going to suggest that some of our design effects are going to be big for the full sample. Okay. Other data sets, maybe you have more cluster codes, maybe this number is going to be smaller. But that's your B in that calculation that Kish was showing. So that's another nice byproduct of this table. Okay. Okay. Any questions about this table or what it's showing us? Definitely pair these commands every time you're setting this up within Stata. Okay. All right, back to the do file. So we have the design variables set globally. Now we can actually execute some design-based analyses. Okay. So what we're doing here is we're computing 3 sets of proportions. Okay. Now notice, I write these all one line at a time. Okay. If you were to list all of these variables in one call to prop, okay, Stata is going to use list-wise deletion for that analysis. And it's going to throw out cases with missing values on any of those 3 variables. So when you're doing this kind of descriptive analysis, always best to do it one at a time, because then you're making maximum use of the information on each variable. You're not losing cases with missing values on any of the variables. Okay? So when you're doing these descriptive analyses within Stata, make sure to run the commands one at a time.
Would you put the 3 variables together at the same line?
That's what I'm saying. That would invoke
Okay.
list-wise deletion.
You could put, but
It's a bad idea.
okay.
Because your estimate for, say, one of the categories of gender may be based on throwing out cases that actually had a value on gender. We want to avoid that. Yep. So that's why we're doing this one at a time. Now, the nice thing about this, again, once you have those design variables set, all we have to do is add SVY colon to our regular analysis command, and we're going to get weighted point estimates, and we're going to get linearized variance estimates. Okay? We're executing the fully design-based analysis for each of these 3. So I'm going to run these commands all in one block here. And I'm going to see 3 different sets of output when it actually finishes running. It'll take a second the first time that you run these. So see, right now, it's calculating those weighted point estimates for each of the categories of HCAT and calculating their linearized variances in the background using those formulas that we talked about. Okay? Then it's going to do the same thing for the other categorical variables. And you see these 3 tables of output, which are going to be saved in our log as well. Now, we can say these are unbiased estimates of population proportions in each of these categories. So we could say a weighted estimate of the proportion of the population that's in H category 2, which remember was like between 18 and 30, is 44.6%. Here's our linearized standard error, which it explicitly says within Stata. And then you see what's called a logit confidence interval. We'll talk more about that when we get to categorical data analysis. But this is a slight transformation of the design adjusted confidence interval to make sure it stays between 0 and 1. Okay? If we had a proportion that was say 0.01 or something like that, and the standard error was 0.02, we don't want the lower limit of that proportion to be negative, because that doesn't make any sense for proportion. So this logit transform is used by default in Stata to ensure that these numbers stay between 0 and 1 when you form the interval. Okay, but that is the information that we would report in a technical report or a paper or something like that when we're trying to make statements about the larger population. And again, we do not want to say that 44.6% of the sample is in age category 2. That is an incorrect statement. Okay? We're estimating that 44.6% of the target NHANES population is in age category 2. Okay? You got to be very careful about how we talk about this. Okay? Same idea for gender. So we estimate that 51.2% roughly of the population is female, 48.8% is male. Okay, we see the corresponding standard errors. And then for education category, we have these 4 different categories of education. These are our population estimates of the distribution on the education variable with their corresponding linearized standard errors. Okay. So for this type of descriptive estimation, as long as you've taken care in how the variables are formed, recognizing missing data, you've read your documentation very carefully to identify the design variables, it is mindlessly simple to do these design-based analyses correctly. Okay? All the work is being done for you by the software. We just have to report this and interpret it correctly. Write this up. Okay? So that gives us our descriptive estimates of these proportions, maybe as part of a larger descriptive analysis task. Okay. One cool thing you can do within Stata is create a new category variable using this EGen that stands for extended generate, creating a new categorical variable that combines or cross-classifies categories on age, cat 3, and gender. So we'll look at each possible combination of age, category, and gender if we want to create a new grouping variable like that, and then calculate weighted estimates of proportions within each of those categories. So we're going to see age group 1, sex 1, age group 1, sex 2, and then age group 2, sex 1, age group 2, sex 2, and so forth in the 6 new categories. So if we want that kind of cross-classification of the population, we can use this grouping function to do that, given 2 categorical variables. So this EGen will create that variable in my data set. So I now have this variable called age sex. And then I'm simply going to apply SVY prop to that new categorical variable to get population estimates within each of those 6 categories. And I could apply a label to them. I could really do whatever I wanted with those categories, but I at least now have that variable available for descriptive analysis purposes. Okay, everybody with me? Questions, comments on this so far? Yep. Say louder, I can't.
The label of age value.
Yeah, so in Stata, under data management, there are these different utilities. So you can assign value labels to variables. Like that's one possible way to do this. What you do in this case is you assign a specific value to a string definition, and Stata will then apply that to that variable. So like if I choose this particular option here, let's see, I have to define the value label first actually. So let me do that. Manage value labels. Okay, so I'm gonna, in manage value labels, I'm gonna create a label. I can call this like age, sex as a general label. And then here's where you can say, I want to call category 1. Oops. Call category 1 age, let's see here. Age, what did I do? I did this, it was age by sex. So this is young males. Okay. And then I can call category 2 young females. Category 3, middle, males. Category 4, middle, females. Category 5, older, males. Category 6, older females. Okay. Now I have that value label definition saved in memory. Now I can assign that particular value label to that new age sex variable. So I can assign value label to variable. So for this variable age sex in my list, I'm going to assign the value label age sex from the list that have been defined. Then I say, okay, now, and then this is one of the things I like about Stata. Anytime you set something up by the menus, you get the syntax echoed. So I could copy this syntax into my do file if I wanted to for this kind of assignment. So I have a memory of how I did that previously. Now, if I rerun that survey prop in the table, I get more meaningful definitions. Right? Any questions about that process? So usually, if it's something I haven't done in Stata before, I'll set it up by the menus to begin with, and then just save that syntax for future use. Okay. Back to the do file. Now let's look at a mean. Okay. So now we're taking this income to poverty ratio for each of the individuals, which was another NHANES variable as a measure of socioeconomic status. And instead of using SVY prop, I'm going to use SVY : mean to generate a population mean on that particular variable for the full sample. Okay. So simply run that command for mean. Now I get a weighted estimate of a mean and a linearized standard error. And you can see that this is a pretty precise estimate for the population of what this average is on this socioeconomic status index measure. And remember, within Stata, and I'll do this in the do file so you can see, if you want to see the design effects, after you run an analysis command, just say estat effects. Okay. I added that command here below survey mean. I'm going to go ahead and run that. That's going to give me a table in a second here, showing me both the def and the deft. Okay. Def, DEFF, is the design effect, the ratio of variances. Okay. DEFT, that's the ratio of standard errors. Okay, so this guy is just the square root of this guy in estat effects. But this guy should give me significant pause, right? That design effect for this mean is 34. So you look at that and you say, NHANES, what are you doing with the sampling error calculation model? Okay. Based on the 31 clusters that you gave me, the 14 strata, the weights and their variability, you're giving me point estimates that have a design effect of 34. Am I doing something wrong? Hey, what's going on here? NHANES is going to get back to you. Nobody using NHANES data is doing full sample analysis. NHANES is strictly designed for subdomain analysis, like we talked about on day one. African Americans, elderly individuals with disabilities, so forth and so on. Many different subpopulations are oversampled. There's all kinds of variability in the weights. Seldom are full sample estimates going to be reported. Okay? They'll say, yeah, the full sample estimate has a huge design effect, but we never intended for NHANES to give you these. NHANES was designed for domain estimation. So that's why we're seeing this. Okay? But even despite that huge design effect, we still have a pretty tight confidence interval, right? So even with that huge variance inflation, that linearized standard error is still resulting in a relatively tight confidence interval for what we want to say about the population. So just because it's big doesn't mean we shouldn't account for it. But this is an indication that this really isn't what NHANES was designed for. It was designed for subpopulation analysis. Okay? And that's what the next sequence of commands is doing here. Okay? This sequence of commands is now breaking down this particular estimated mean for different subpopulations defined by these categorical variables. Okay? So the over option for these descriptive analysis commands says, repeat that descriptive analysis for each category of these variables and do it unconditionally. So don't delete cases that are not part of a given subgroup, but process the entire data set to calculate standard errors. Right? So over is another example of a valid subpopulation command to use when you're doing these kinds of descriptive analyses. We're not using if or by or anything like that. We're using over to do that kind of analysis separately for each of these groups. So if my research question said, how does the mean socioeconomic status vary depending on your category of education? This is the kind of procedure I'd want to start with for descriptive estimation. They show me the weighted point estimates of the means for each category of education, right? So let's run this first line for this subpopulation analysis. And so you see in the output, okay, we get weighted point estimates of each of these particular means, okay, and their linearized standard errors treated unconditionally. Okay, so again, we're not deleting cases that don't fall into category 1 or don't fall into category 2 when these are being computed. We're reading in everything and doing the variance estimation based on everything. Okay, now let's look at the design effects. So after running this command, I can say estat effects. Look what happens. They're cut by a third, maybe even more. Okay, because these design effects are going to be lower for subpopulations. They're still pretty big. The ratios of the standard errors are varying between 2.5 and 5. So they're still pretty big in terms of variance inflation, but you look at these confidence intervals and even glancing at the overlap here in the intervals, you see there's pretty significant evidence of differences between these categories. So roughly, informally, if you just look whether the intervals overlap, there's a difference between 3 and 4. It looks like categories 2 and 3 overlap to some extent. Looks like categories 1 and 2 overlap to some extent, but we probably conclude that 3 is different from 1, 4 is different from 1. So we're going to talk about how to do all those kinds of pairwise comparisons next week, but this is at least giving us initial sense of whether or not these education subgroups are different from each other. So it seems like we still have reasonable power to pick up on these differences despite the big design effects.
What does this variable means?
The income to
What does it mean?
which variable?
This one.
Which one? Sorry.
NGFM.
This is income to poverty ratio. So this is a measure of your income relative to a poverty threshold. So kind of in a standardized fashion, how much higher than the poverty line is your income? It's kind of a ratio idea. So 1 is like you're right at the poverty line. So it's an index of socioeconomic status. Yep.
Should we generate a graph?
Quick question. So
Wait, hold on, Sarah. Sorry, it's kind of quiet here. So there's a question in the room, Sarah, and then I'll come back to you. So can you say it a little bit louder so people online can hear?
So the survey means and before we do that, shouldn't we generate a
No, it's not necessary in this case. Remember, we're being non-parametric. Everything about this design-based approach is non-parametric. So we're just computing a measure of the central tendency of this variable. This does not rely on the assumption that that variable is normally distributed. We're just computing a mean, that's all. Okay, Sarah, yep, you had a question?
I do. This might be slightly technical. So your variable, the income to poverty ratio, is that for each sample, their average, their income divided by some ratio of poverty level, right? So you'd have some people low, some people high, and then you're taking the average of over all the sample of those to get an average sample, correct?
Right, that's what we're doing, yep.
I know that for some of the data I've worked at, they oftentimes they'll say instead of taking an average of ratios like that, for example, the debt to asset ratio of each individual, if you take an average, you could get really interesting effects because you get high and lows. Instead, they take kind of the sum of everybody in the numerator and denominator, and then use the average, use that calculation. You run into that factor here of just extreme values.
There could be extreme values, right? But you know, I think you're going a little bit farther than we want to go right now. We're just showing these descriptive approaches. Okay.
Okay.
If you think that the distribution is very skewed, okay,
Mhm.
you could calculate a median. There's
Yeah.
other measures of central tendency that we could compute, but we haven't talked about computing quantiles yet. We're just starting simple here with the mean. Next
Okay.
week, we're going to talk about how to compute functions of observed variables, like I think you're referring to here, and how we can compute variance estimates for those. But we're
Okay.
just starting very simple here with the mean of a continuous variable. That's all.
Thanks.
Yeah, so for these financial data, it's often the case, right, that a distribution might be very skewed. So like if we look at a histogram, I can do that just by typing hist and then the name of the variable, which in this case is INDFMPIR. Okay. Again, unweighted. I showed you how to do the weighted in the lecture notes, but just to get an initial idea of this distribution, look at this distribution, right?
Mhm.
Does this look like a bell-shaped curve? Not even the slightest, right? All we're doing is computing the mean to see what the average looks like. But if we were going to fit a regression model to this variable, something like that, we definitely have some concerns about any kind of assumptions of normality moving forward. Okay. But we're just taking a simple population mean for the variable right now. Okay. Okay. Let's look at the same subpopulation estimation for age categories to see what we see for differences among the age groups. Okay. Again, looking at overlap in the intervals, not very strong evidence of differences between 3 and 2 and 2 and 1, but it does seem like there's a difference between 1 and 3 in terms of the mean poverty to income ratio value. Okay. So again, nothing formal yet. We're going to talk about being more formal next week with these kinds of comparisons. But so far, we see some initial evidence of these differences. These kinds of analyses would be used to populate tables of descriptive estimates, means, proportions, all that kind of stuff to give people a picture of what the population looks like. Formal statistical comparisons of these means, we're going to get into that next week. Okay, let's look at differences by gender using over. See if there's any evidence of a difference here. Okay, very similar intervals. Okay, these overlap pretty heavily, so there's no strong evidence of a difference between males and females in terms of this overall mean. Okay, what about by those 6 different categories defined by age and sex? Now that we have those nice labels in there. Okay, now you can take a look at these and see where there might be differences. So for example, if we compare older females to young females, it does seem like older females are in fact different from young females in terms of this poverty to income ratio. Not a big surprise in terms of age relationships with measures of income. We can at least get an initial sense of what those differences are. Now, I want to show you an example of what will happen, again, if you take an incorrect approach to this kind of subpopulation analysis. So suppose I was to say, survey mean of this income to poverty ratio, oops, if age sex is equal to 1, and let's say our subpopulation, we want to further define by whether or not people have an irregular heartbeat as a health condition. Okay, so I'm saying I only want to limit this analysis to people who are younger males and they have an irregular heartbeat. And I want to see what their average poverty to income ratio is. Okay, look what happens. Now I'm estimating a mean where Stata says no standard error for you because you gave me a sampling error calculation model where one stratum has only a single PSU. Okay. So Stata by that default in survey set is saying you don't get a standard error. I'll give you the point estimate, but you can't make any kind of inference. Okay. And I can dig into this problem a little bit further to see what's going on by using a conditional version of survey describe. I can say survey describe if age sex is equal to 1 and irregular is equal to 1. Okay. That gives me a conditional table of the sampling error calculation model. And it says for this very unique subpopulation that you're interested in, there's only 4 strata with sample present. And among those 4 strata, 3 of the 4 only have 1 sampling error cluster code. Okay. So we're in a very bad situation for linearized variance estimation. But let's look at the alternative. If I do this unconditionally, and I say survey subpop, if age sex is equal to 1 and irregular is equal to 1, and I get rid of that if condition, what's the difference? Instead of using if, I'm formally using the subpop option for this particular analysis. Oh, I now get a valid linearized standard error for that subpopulation. All those other clusters in the design are being treated as sampling zeros. Okay, there was no sample present in any of those clusters for that subpopulation, but for the purposes of variance estimation, they're being treated as totals of 0. And that's where we're getting that standard error. Now, it's a huge standard error because it's such a tiny subpopulation. How many observations are there in the subpopulation? 6. Right? This is not an estimate that we're going to be putting in any kind of report, but the point stands. Okay? You might be interested in a subpopulation of size 150 or something like that. And you might run into this problem if you're not careful about how the subpopulation is specified. And again, this is all only for linearization, right? Only relevant for linearization. Okay, so that takes us to the end of the Stata code for today. You can then, when you're done with the given Stata session, highlight log close, and that will close the active log that you have open. So output code is not going to continue to be appended to that log. That closes that log, and now you could look at it in a text editor or something like that to see what you've generated as a part of this session. So if I close this log right now, I'll see this echoed in the Stata results window. It tells me exactly when it was closed. That's also going to be put in the SAS output, or I'm sorry, the Stata output. So that'll also be saved there, so you know exactly when you finish this analysis, so forth and so on. That timestamp will be included. Okay. Okay, so questions about Stata? Yep, Jupiter.
Sorry, can you just clarify just the difference between over and sub?
Right, so over, the over option is going to repeat the analysis for all possible categories of some variable. Subpop is only going to give you output for the one subpopulation that you specified. So what I just specified there, I said I wanted young males with an irregular heartbeat. That's all I care about. So it's only giving me one estimate for that one subpopulation. Over is going to repeat the analysis for all possible categories. Yep. Weston, do you have a question? Okay. Any other questions about the Stata code before we take a break here? Other questions? Okay, all right, I think we'll break then to about 10 after, so it's about 11:05. And then at 10 after, I'm gonna get started with the R code. So we'll walk through the analogous R code in our studio and see how we can replicate these same results using the R survey package, okay? Okay, so I'll pick back up at 10 after.
About NHANES.
Mhm.
So they provided in Route 6 documentation, they provided the final weights
Mhm.
of the replicates as well. They use PR. So I'm not sure which one I should use, even though I think that should be the final analytic weights, but I don't understand the reason for it.
For variance estimation. So all it takes is one variable from round 6 that was measured in round 6 to require you to use that one. You could be merging in variables from rounds 1, 2, 4, it doesn't matter. All it takes is one variable from round 6, because the analysis is going to be limited to people with valid values on that round 6. That's going to be like your lowest common denominator for determining the sample size. So that requires you then to use that round 6 weight in addition to whatever replicate weights they provided for people in that particular. So that's why, like what you highlighted, even if you're looking at people who had certain characteristics in round 5, and you're analyzing an outcome in round 6, you have to use that round 6 weight. And then if they give you replicate weights for round 6 individuals, just use those for your variance estimation, so they can put them in a survey set or whatever software you use.
So if I didn't know about this, and I decided to go for the final to declare with the final analytic weights and Route 6.
Yep.
My computation would be very different.
Well, you have to use the replicate, so I'm not sure what the alternative is. Yeah, so if you don't put the replicate weights on, it's just gonna use linearization by default. You're not gonna account for any of the design features. You're only gonna be accounting for the round 6 weights. So you have to put those replicate weights on to fully adjust for the design features.
Even though my design is cross-sectional.
Cross-sectional longitudinal doesn't matter, it's irrelevant. The replicate weights are the way that you're fully adjusting for the stratification, everything else that went in outside of the calculation. It's crucial.
So I don't yet understand this section here. It says that in round 1, interest rate equal 75, is that because they take into account the years of 6 and 6?
I don't know. I mean, that's something specific to NHANES, so I don't know what the rationale is there. The basic approach should always be, it's kind of like with using NHANES with the medical exam weight. All it takes is one variable from that medical examination to require you to use that weight. So if round 5 is your most recent round, for example, all it takes is one variable from round 5, you gotta use the round 5. If round 6 is your most recent round, all it takes is one variable that you're analyzing in round 6, you gotta use it. That's the principle.
You're gonna have it for You're gonna need it for TV. For example.
Then you end it. Once you like, want to change your brand, everything is perfect. Yeah. For example, then you can get another flavor. Let's just say I get this. For example, I added that one. This one. Okay. Yeah, so like $30. So I have to sign up for it. But anyway, it's gonna be fair about it. But you need to sign up for it.
Yeah, real quick, we're about to start with it.
I was just preparing my data set regarding this option word perspective in that set. So I prefer like this. So I have different standard variables for so maybe I need to reduce after the inside possible variables. So I have given that frequency. So these are the possible observations. But if then like I just as minus and get the missing observation, and after even after the code, I have get the same answer, like variable connectivity and comma missing. So basically, this is because the non-response question. So like this way, is it is fine. I'm just giving the observation and the missing observation. But I'm just like analyzing the variable with complete.
So that's why I said at the beginning. You have to create an indicator in your data set, looking at all of those variables. So across all of those variables, if there's at least one missing value, they fall into one. If across all of these variables, if they're complete data, they fall into a second. Okay. So you're creating a new variable in your data set. It's a 1 for the cases that are complete and a 0 for everybody else. Okay. Once you have that new variable, you're just comparing those two groups, t-tests, chi-square tests, in terms of fully observed variables, like these first two, like that one, like these. That's all it's asking.
So I need to like perform any basic analysis.
It's just very basic, yeah. T-test, chi-square test. Doesn't even have to be designed.
Just to have insight about the data.
Get a sense of whether the complete cases are systematically unique compared to the incomplete.
And then I have like this population. Like I have a target population between 1 and 70. Then I categorize it 3 for check. So is it like fine?
Yeah, that would be for an over, but this assumes that all of your analyses that you're planning are going to be repeated for each of those 3 groups. If you just care about one of these 3 groups, just focus on that one.
Yeah. So I can split it into 3 further categories.
If you want, it depends on your research question. Okay. Okay, let's pick up again here, and we're going to shift gears now and turn to the R software. Okay, so a little bit different from how Stata operates, but we're going to see how you can use commands and functions within R to basically replicate the output that we were obtaining within Stata. Okay, first things first, R again is free software, and when you're setting up for these kinds of analyses, you do have to load some contributed packages. Okay, now loading contributed packages is really a 2-step process in R. First, Sarah, did you have a question?
Oh, sorry. Okay.
Okay, yeah, if you could mute, that'd be good because we're getting a lot of background noise. Yep. Okay, so first things first, with loading contributed packages, you have to first install the package. RStudio makes it very easy to do that. If you don't have the 3 packages that I've listed here at the top of the lab notes, you can go to this packages tab and notice it says install as one of the tabs here within packages. You can just click on that install tab and then type the name of the package that you want to install. Okay, that will make that package available for you to load within RStudio. It doesn't turn it on. It just makes the software available to you when you install it. To actually turn on and load the functions within these different packages, you have to use these library functions within R once you've installed them, or you can use the require function. That's another function that will load the contributed package for you. Okay? So for this particular lab, we're going to load the Haven package, the Dipplier package, and the survey package. Haven and Dipplier are really for data management. Okay, survey is what we're really using for all of our design-based analyses. And survey is not part of the base R installation, so we do have to load that as a contributed package to make those functions available. Okay, so you run all of those on this version of R Studio and R that I have on the machine here in the classroom. The version of R is a little bit older. That's why I'm getting these warning messages saying that there's a newer version of these packages available, but that's all right for our purposes today. Okay? But we do have to make sure that all of these are loaded to start with. Okay, then the next function here is called read DTA. This reads in a Stata format data set and saves it as an R data frame object. Okay? There's different ways you can get Stata in there. Okay, this is in the Haven package, this particular function. This is just one possible way to read in Stata data, but that's how we're getting that NHANES version of the data set into an R data frame object. Okay, and when you look at, or when you're able to load and create that particular object, you can type in the R console or in your script, capital V view, and then the name of that object. Okay, that's going to open up a data editor that you can take a look at. Okay, just to get a feel for the data set, look at the different variables, scroll through the different cases, etc. Looking at the possible values, looking at missing data, things of that sort. That'd be like opening up a data editor within Stata to actually look at the actual data. Okay, so that's something I like to do anytime that I load a new data set, just to make sure that I'm not getting any surprises. Everything looks like I expect it to look. Okay. In addition, going back to the R script here, the analog of that lowercase command within Stata is this to lower function within R. So this is another very helpful command because R, like Stata, is case sensitive when you're typing variable names. So to lower takes the column names of the original data frame object, puts them all in lowercase, and this is just overwriting the column names of the original NHANES data frame object with the lowercase versions of the column names. Okay? Just makes it easier to type things out if everything's in lowercase. Optional, but makes your life easier so you don't get any weird errors when you're forgetting a capital letter somewhere or something like that. Okay? So that just changes that element of the data frame so you can work in lowercase. Okay? So this is going to be the general structure of the lab notes. We've tried to the extent possible to exactly replicate the commands in Stata and R so you can see exactly how to do the exact same thing within the two different packages. Okay, and that's to a certain extent what we've tried to do on the ASDA website as well. Okay, so we're going the exact same pattern here. So to start to look at initial frequency tables within that particular data frame object, we can use the simple table function, which is part of the base R installation. And notice that we're saying NHANES $age. This is referring to the age vector within the NHANES data frame object. Or in other words, the age variable within the NHANES data set. Okay. So we use that $ to refer to specific variables within a data frame object within R. So this is referring to the age variable by itself. And then this option for the table statement says include NA values in the frequency table. Okay? In R, like in Stata, we saw the missing values were dots. In R, the missing values are going to be capital N, capital A's in the data frame objects. So this says if you see an NA, include it in the frequency table. Don't throw it out. Okay? So that's the analog of the missing option within the tab statement in Stata to make sure that missing data is included in the tabulation. So I'll go ahead and run this line. So when you're running these lines within the R script, just highlight that line, and then there's a little run button up at the top of the script window. That will run the one line that you've highlighted within the script, much like we were doing within Stata. Okay. Now, in general, output in R not going to be as pretty as we see in Stata and SAS and some of the other packages. R isn't trying to make output beautiful. R is just trying to do stuff correctly and put it in the hands of data users. Okay, so not that clear of a frequency table, but you're still, when you boil it down, seeing the same frequency counts for each possible value of age that's available in that object. And notice we asked for the NA to be included. So R is explicitly telling us here that, sorry, I'll get this cursor out of the way. R is explicitly telling us that there are no NAs on this variable. So no missing values. So that's a good thing, right? Like we saw in Stata. Stata didn't even have a missing row in it because there was no missing data. But even if you ask for that, you're going to get a 0 count here within R. So that's helpful to confirm that this variable has no missing data. So you can repeat that table function again as an initial descriptive step for all of the other variables in your data set, just to get a sense of the missing data. Okay, next, some of you may or may not be familiar with pipe operators. Okay, the pipe operator is taking a given object and pushing it forward into another function. That's the basic way that it works. The pipe operator is this percent, right hand arrow or greater than sign, if you will, percent combination. So it's taking this object, pushing it forward into this particular function, and whatever result gets created from those pipe operators is saved in this new object. Okay? So what we're doing here is we're taking this NHANES data frame object, we're doing something to it, and then we're overwriting the previous object with the new version that includes whatever we did here. And what we're doing here, I've always struggled with this mutate function. It's an ugly sounding function, right? But what it's doing is it's just a function that allows you to change variables or create new variables, okay? We're basically implementing that same recoding process that we talked about within Stata with gen and replace, okay? So mutate, again, is this general function that allows us to create new variables. We're creating a new variable called AgeCat3, which is taking on different values depending on the arguments to this if-else kind of nested sequence here. So just take a careful look at this. We're saying, using this if-else function, if the condition is true, the result takes on this particular value, 1. Okay, so if we're between 0 and 18, we get a value of 1. If that condition is not true, go to the next argument, which is another if-else function. Okay? That says if age is between 18 and 51, we're producing a value of 2. That's not true, go to another if-else function. If age is greater than or equal to 51, they get a 3. Otherwise, there's a missing value. Okay? And all those end parentheses kind of close that series of conditions as a part of the mutate command. So what this is basically doing is creating a new AgeCat3 variable in NHANES and creating a new data frame object that takes this in addition to that variable. Okay. It's a little bit long-winded, but that's the way we're adding that variable to the data set. Many other ways you could create recodes within R. This is just one possible approach.
Does R treat missing values as values?
Right, no, they're not ordered like they are in Stata. So it's a completely different approach to it. It's just a missing value. And R's default is really to ignore it rather than treat it as having any kind of ordered value in a sense of order statistics. It's just a missing value. And most procedures will just stop if there are any NA values on the variables of interest. You always have to say how you want to handle the NA values. Okay, so it's different from Stata in that regard. Okay, so I'm going to run this entire block here to create this new version of the NHANES data set, adding that AgeCat3 variable. Now I can go back to my view of NHANES, scroll all the way to the right, and I'll see that new AgeCat3 variable. Okay. So again, one way to add those new variables, there are many others, but that's a popular way using these particular packages. Okay, so you can create other variables that way. Again, I'm going to look at a frequency table for that new variable I just created, allowing for NA values, and confirm that there are no missing values on that new variable as a part of that recode. Okay. Now that I'm happy with that, I can create what are called factor variables within R. These are variables that in subsequent analysis commands will be treated as categorical and not as continuous. So R's default is going to be to create or treat every numeric variable in the same way in various analysis commands. by declaring particular variables in a data set to be factors, they'll be treated as if they're categorical in all subsequent analysis commands. This is usually a very handy step in terms of managing your data within R, so that you don't have to do this down the road when you're fitting models or something like that to declare variables as being categorical. Just declare them to be categorical by definition in the data set. That's what these factor functions are doing here. So again, we're making use of mutate. We're taking the current version of the NHANES object, we're sending it through this mutate function, and we're just redefining each of these three variables as categorical factor variables in that mutate function. Okay. So I'm going to go ahead and run this block again here. Now, moving forward, HCAT3, gender, and EdCat are going to be treated as factor variables in subsequent analysis functions. They'll be treated as categorical. Okay? And I'm just overriding NHANES once again. Now, if we want to do what eGen with group was doing within Stata, we again can use mutate, but we're using this colon to really define all the cross classifications between these two categorical factors. And that's going to create a new categorical factor called HSense. So this is the analog of eGen with group within Stata. If we want to create a new variable that contains all the cross classes of two other existing factor variables. That's why we set them as factors first. Okay. So again, I'm mutating, just adding that variable to the overall NHANES data frame object. Okay. Once we're happy with the variables that we've created and we feel that we're ready to proceed with analysis, in Stata, remember, we use survey set to globally define the design variables. In R, we're creating what's called a survey design object, okay, containing the design information. And we do that using the SVY design function within the survey package. So we need to have that survey package loaded before we can use this particular function. Okay? Now, how does the survey design function work? First argument, and you can order these arguments in whatever way you would like. Okay? First argument is strata. And we say that the stratum sampling error codes are defined by this particular variable with a tilde in front of it. Okay? Anytime we're specifying variables to survey type commands, we need to make sure that variable names are preceded by a tilde. It's another very common source of errors when you're first starting to use these functions within the survey package. Okay? So this is saying that the stratum codes for linearization purposes are contained in the variable SDMV_str. Okay? Just like we have within Stata. Okay? Second argument after a comma is ID. And again, a little bit of a misnomer in the way this is labeled here, but ID, these are the PSU IDs, or more generally, the sampling error computation unit IDs, the clusters within each of the strata. So this is where you would specify the cluster variable, the variable containing the cluster codes after a tilde. Okay, so we're specifying SDMV PSU after the tilde. That sets the cluster codes. Third argument is called weights. This is where you specify the final survey weights that you want to use for your analyses. So after a tilde, we're using WT MEC 2-year. Okay. Fourth argument is the name of the data frame object that you want to use with all those variables that we've created. And that data frame object contains the variables that we've specified here. The stratum codes, the cluster codes, and the weights. That's the fourth argument is data. And then remember from lecture, the fifth argument is nest. That says that the PSU codes are nested within the stratum codes. Okay, for the sake of ANSYS submission. We do have to specify that within R. Make sure that those codes are handled correctly. Okay. Now, as a reminder, when you use survey design and you create these kinds of design objects, linearization will be the default for variance estimation. So if we plug that design object into a survey analysis function, it's going to default to linearization for variance estimation. All right, so I'm going to run this block to create the survey object, survey design object. Okay. Now I have this object called NHANES SVY. Like survey describe, I can then say summary. I'm going to type this in the script actually. Summary then in parentheses, the name of that survey design object. Okay, I'll run this line. And what this is going to do is give me a high-level summary of what is contained within this design object. So one of the cool things I like about what our the survey package within R is doing is it's reflecting the sampling area calculation model, right, and the assumptions that we're making. So we assume that we have a stratified single-level cluster sampling design with replacement. This is spelling out the assumptions that we were talking about in Module 3. We assume we have a stratified with replacement sample of ultimate clusters, where we're taking every single sample element within those ultimate clusters. Okay? So I like how Lumley programmed that. It clarifies you have 31 clusters in total. Okay? Echoes the design call, gives you the probabilities of selection. Okay? Some probabilities are tiny. Okay? Remember, these are probabilities, not the weights themselves. All R is doing here is inverting those weights and turning them into probabilities. Okay? So it gives you kind of a descriptive summary there with some giant values. And then for each of the different strata, you see how many PSUs are available in addition to the sample size. So very much like the SVY described within Stata, this is giving you a summary of those design features. Just to make sure everything looks okay, we want to make sure that there are no strata with only a single PSU present. Okay? When we're looking at this. And again, we can get a sense of what replication techniques might be available based on the available number of clusters within each of the different strata. All right, then it summarizes each of the variables in the data frame object. So these are all the variables that were brought over from the data frame object into this design object. So you get a sense of what variables are available for subsequent analysis commands. Okay. So that's like the analog of survey describe. Okay, everybody with me? Questions so far? Questions?
I have a very simple question.
Yep.
The weights that log the interactions and
Yep.
to YO. This is the weight that's considered in the survey related to non-response rate.
Right. Right, yeah, those are the, so what we're specifying to weight, that's the final overall adjusted weight, base probabilities of selection, non-response adjustment, calibration, that's the final weight that reflects all those steps. Yep, George?
In the assignment, when I was trying to do that app, was a particular point where it was giving me an error, and then it was asking me if the weights were correctly
Right.
When the sample sizes, I couldn't understand.
Right. Lumley hates normalized weights, much like I do. So he is explicitly pointing out an error message when you do that, saying you are not giving me population scale weights. That's what that was. So technically it's just a warning, but he's of the same mindset. There's no reason whatsoever for any survey right now that you should be inputting normalized weights to this procedure. He's letting you do it, but he's giving you a pretty blatant warning that says you're going to have some issues. And again, as we discussed, that's going to prevent estimation of totals. Everything else should be fine. But for example, within R, if you input normalized weights, it breaks all the design effect functions. He's fully expecting design effects to be able to produce effective sample sizes. And with weights that sum to the sample size, he can't do that. And so it's kind of knocking you on the head and saying, you're not giving me population scale weights. That's what that means. Yep. I had a good chance like during my sabbatical. So R was born at the University of Auckland in New Zealand. And I had forgotten about this. So I had scheduled meetings with Lumley at the University of Auckland, where he's a professor, just to talk about like what his current thoughts and plans are for the survey package. And when I walked into Auckland, there's a giant banner that says, "Welcome to the Auckland Statistics Department, the birthplace of the R software." I was like, oh, that's right. I totally forgot about that. I was like, wow, I feel like I'm walking on hallowed ground. but yeah, he has very similar mindset about like what, what people should be working with these kinds of variables. He hates normalized weights. Like he automatically discounts them if he sees them in a survey and says, I can't do anything with these, because for his work, a lot of it involves estimation of totals. It drives him nutty when data producers give you normalized weights. Anyway, that's an aside. Okay, that's why he programmed that here. Okay, now suppose, again, the default in the survey design object is linearization for variance estimation. Suppose you wanted to create replicate weights kind of on your own, on the fly, as I was saying in the lecture. In the survey package, there is a function called as.svRepDesign. Okay? In the lecture notes, we talked about how you can use svRepDesign to just read in the replicate weights, if that's what the data producer has given you. Okay? As.svRepDesign takes an existing survey design object that was prepared for linearization with the stratum and cluster codes and creates replicate weights for you to be saved in a new survey design object. Okay? Now, the replicate weights created only reflect those adjustments that we talked about in lecture on Wednesday. Simple upweighting to account for cases that were deleted when the replicate was formed. This does not automatically apply non-response adjustment, post-stratification to each of the replicates. It just creates the replicate weights as they are. Okay? So you do need to do a little bit of additional work to create those adjustments for each of the replicate weights in this data set. But this is what you would do to create those kind of what I would call base replicate weights given the stratum and cluster code information. And you can tell as.svRepDesign what type of replication to use. And so here I'm saying JKM for that general jackknife, delete one at a time approach with the clusters. Why? Because that's one of the only ones that's available given this sampling error calculation model. Like I can't use BRR, right? So if I run this, I now am going to have a survey design object very quickly called JKN that includes replicate weights. And if I say summary, I've already looked at summary of NHANES survey. If I say summary of JKN, that's the name of my new design object with the replicate weights. I run this, oops. Okay. Now, instead of saying what the sampling error calculation model was for linearization, I have a stratified cluster jackknife with 31 replicates. Follow the JKN technique. Okay. So I can flip the variance estimation on the fly if I want to, okay, for whatever reason. Okay, so now we have these two different design objects, so we can use either of them if we wanted to in these subsequent analysis commands. We could use the linearized object, or we could use the jackknife object. We can compare results if we want to. Okay. So how do we run the actual analyses within R? Once you have those design objects created, then you can use the SVY functions that are available within the survey package. So if we want to look at means or proportions, okay, we can use SVY mean. I know that sounds a little bit weird, but SVY mean can take factor variables and give you a table of estimated proportions. And again, a little bit of a misnomer, but the variable, assuming I've declared it to be a factor already in the previous data management commands, if I input a factor variable here as the variable of interest, survey mean will not give me the mean of those values. It will give me estimated proportions for each category. So that's how I get to those kinds of proportions. If I use survey table, I get a table of estimated totals. If I want to see proportions, I have to use SVY. Okay? So again, after tilde, make sure your analysis variable of interest as the first argument comes after a tilde. Second argument to survey mean is my design object. I'm using the linearized design object in this case. Okay. And notice that every time, all of these functions, I'm always saying what to do with NAs, missing values. I didn't have to worry about that in Stata, but R always kind of short circuits if it sees any NA values on a variable of interest. So NA.RM is just saying remove any cases with an NA value on that variable from the estimation. Okay, and you kind of say, well, yeah, of course. Like, why wouldn't we just do that by default? That's how the survey functions work. That is not the default. By default, the survey functions are going to give you an NA for the result if there's any missing values on the variable of interest. So NA.RM always just says take those missing values out and use what's valid as a remainder. So given I've already declared AHCAT3 to be a factor variable, I'm going to highlight this line, run it. Now I see the exact same weighted estimates of the proportions. Again, kind of a misnomer. They're labeled as means. We know they're proportions, but when you think about it, that's the mean of a binary variable, right? So it's the mean of each of these binary variables and then the corresponding linearized standard errors, which are replicating what we saw within Stata. Okay? If I want confidence intervals for each of those means, I simply wrap that entire function in the confident function. Okay, I take the output from that function and use confident, where the default is going to be a 95% confidence interval. I can change that alpha value within confident if I want. Okay, so after using confident with that exact same function, that's where I'm going to get those design-based 95% confidence intervals with the right critical t value, the linearized standard error, and then using the weighted point estimates. Okay, so kind of a two-step process here. If I want confidence intervals for proportions with like a logit transformation or some of the other options that are available within this SVY-CI prop function, I can use SVY-CI prop. We'll come back to this when we talk about categorical data analysis. And then the first variable for SVY-CI prop is an indicator variable that you want a proportion for. So this capital I function is saying create an indicator variable for all those cases where if this condition is true, the respondent gets a 1. If that condition is false, they get a 0. And NAs will be automatically accounted for. All right. So I just want to see the proportion of the population that falls into age category 1. And I want to see a confidence interval for that particular proportion with this SVY-CI prop. Okay. And see here, when I try to do this, there's a little bit of a warning message. Cases with 0 weights are being thrown out. Right? Those are young kids basically that have 0 weights. But you see there the corresponding calculation of that 95% confidence interval along with the point estimate itself. Okay. So the reason I want to introduce SVY-CI prop, because we're going to come back to it later when we talk more about categorical data analysis, that's the function that lets us use different kinds of confidence intervals for proportions. And that's going to become important when we focus more on proportions moving forward. Okay. Same thing with gender. If I want to calculate the proportions for gender and then the confidence interval, same sequence of commands, assuming that I've already declared gender as a factor variable. Okay, again, if I haven't done that yet, gender, remember, is a 1, 2 variable. I'm going to get a mean that looks like 1.49 something, okay, which is meaningless for something like gender. I need to declare that as a factor variable first. Okay, so I'm going to run that. I get my estimates, which match data, and I get my 95% confidence intervals. Okay. So this is one of the cool things, and there's a lot of stuff like this in R. You know, if you work for an official government agency or you work for a smaller research institute, and you're trying to make arguments about what software to pay for this area of work, if you're doing secondary analyses of survey data, free software here is giving you exactly what you get in Stata or SAS or something else like that. Okay, so this is a nice feature of R, the fact that Loomly has gone so far to make all of this available, right? So certainly a winning point for R here. Okay, same thing with SVY-CI prop. Okay, to get that confidence interval. Oops, right. Screwed up in my code here. This should be RIA gender equal to 1, not the variable itself. Okay. So then I get my point estimate of the 95% with the warnings about the 0 weights. Okay. Same thing for education. I won't go through and run that, but you get the same basic idea here. And then we could do the same thing for that age sex variable. Declared to be a factor, get confidence intervals. One thing I want to note for those cross-class variables, notice how I referred to specific categories of that variable in those, when forming those indicators. I'm not referring to a specific value. I'm referring to this colon, like 1:1, 1:2, etc. That's the way that that factor version of that variable gets created. It's like a string. So I have to refer to that specific combination of those two values to get that particular point estimate. So if I run all of this here all at once, I'll see the point estimate for that 1-1 combination in addition to the 95% confidence interval. So I'm not saying 1 or 6 or whatever. I have to use that colon like we did in the function. Okay, so key points there. If you want to deal with descriptive estimation for categorical variables, set them as factors first in your data management, and then just declare the variable name to survey mean. And that's where you're going to get the estimates of the proportions. Okay. Now, if we want to handle continuous variables, okay, not much else we need to do. We simply use survey mean, specify the name of that variable after a tilde, again, using the linearized variance estimation object. So I'm going to do that in combination with confident here. And I'll get my weighted point estimate of the mean, the linearized standard error, and then the corresponding 95% confidence interval for the overall sample. Now, if we want to implement what was done with over in Stata, where we were repeating the descriptive analysis for all the categories of some other variable, we would use survey by. Okay, we wouldn't delete cases. We wouldn't form subgroups by deleting cases. We would use survey by, where the second argument to survey by is the grouping variable, in this case, edcat. And the final argument is the name of the analysis function that we want to use within the survey package, which in this case is survey mean. Okay, so we're applying survey mean to that variable separately for each category of edcat unconditionally using this design object, and we're getting rid of missing values. That's what the survey by function is doing here. Again, replicating what we would have gotten from over within Stata. Okay, so I'll run this survey by line. Now what you're going to see is for each category of education, you're going to see the point estimate of the mean and its linearized standard error. And again, we could apply confidence intervals if we wanted to. Okay. Same idea here. If you wanted your grouping variable to just be a 1-0 variable, you again could use this capital I function and create a 1-0 variable for a particular category of education. Okay. Now, if you want to replicate what subpop is doing within Stata, where again, like Jupiter was asking earlier, you're focusing just on one subpopulation at a time, rather than repeating the analysis for every category of some other grouping variable, we use the subset function. Okay, that takes, when we input a design object to subset, we say the first argument is the design object, the second argument is the subpopulation that we're interested in at cat equal 1. So that's the subgroup we want to focus on. Then we create a new design object, which is essentially the same thing, but with that binary indicator for your subpopulation, so that the variance estimation can be done unconditionally. Okay, so subset treats that design object differently than it would for other types of objects. It creates that unconditional indicator. Then in our subsequent analysis command, we just type the name of that new subpopulation design object. That's the analog of subpop within R. That's the right way to do that unconditional subpopulation estimation without deleting cases within the R software. Okay, so if I run this combination of two commands, this is going to give me the estimate only for education category 1, rather than seeing the output for every single category. If I only care about that subpopulation, that's the approach I would take. Okay, so that's the subpop analog. Okay. All right. Now, if you wanted, again, confidence intervals for each of these different categories here, you could use survey by in combination with confidence, right? If you're asking for estimates separately for each category of education, you'll get confidence intervals for each of those different categories. So I can combine all of that at once here to get the different 95% confidence intervals for each of those 4 groups. I can just do that all in one function with survey by. Okay, so that's what these additional commands are doing. Now, the last thing I want to show you, let's just take let's take this overall descriptive estimation for the mean poverty to income ratio, again, based on linearization. Let's see what happens if I replace that design object in the function with JKN, I believe it's called. Yeah, JKN. So now I'm using the design object with the jackknife replicate weights with no additional non-response adjustment or post-stratification, just the replicate weights as they are for variance estimation. Okay, let's take a look at that standard error if I flip the variance estimation technique on the fly. Okay, right? And some of you have already started to see that with your data sets, right? Even with 31 clusters and 14 strata, these are still converging in theory to the same variances. Okay? Even without those additional adjustments. So again, no real reason to get picky about which variance estimation method to use. Just use what the data provider has given you. Okay, that's the key point. Okay. Okay. So that's what I wanted to cover about R so far. Hopefully you have many more questions in mind, but this is our starting point for moving forward to more complex types of analyses, but all using the same basic framework, okay, for defining the design features and then carefully managing our data and then getting into the analysis functions. Okay. Okay, so questions, comments about R? Anybody? Any questions or comments? Very good.
Professor, I would like to ask about the regression.
Yeah.
How can we use the weights that the weight to plug the weights into the regression?
Yeah, so same idea here, Israel. Like we would create a design object, and instead of using survey mean for our analysis, we would use SVY GLM. SVY GLM is a general regression function. We would write the formula for our regression model, then just input our design object, exact same idea.
And now, in this case, it will consider the new weight, that replicated weights.
Yeah, it depends on what design object we input. But right, so just to really quickly show you, we're going to spend a whole week on regression. So we're not there yet, but just to quickly show you, if I wanted to regress, let's see, if I wanted to regress income ratio on, yeah, sure, gender in a regression model. I've already declared gender to be a factor variable. See, that's my model formula. It looks pretty simple, but the left-hand side variable is the ratio. The right-hand side variable is the factor version of gender, not the numeric version. Okay. Then I input my same design object. I don't have to do anything different in that regard. Okay. And then I run this command. It's that simple. That's my design adjusted regression model. Okay. Again, I'm getting a warning about zero weights, but there's my estimated intercept. There's my estimated coefficient. To get the table that you're used to, I wrap this whole thing in a summary function. And then run that command. Okay. There's my table of regression estimate, linearized standard error, p-value for hypothesis testing, p-value. Then I can make inference about these relationships. Okay. So maybe we don't need that week on regression. I just showed you how to do it. But the point I'm making is that it's really that simple. Okay. The most important thing is being careful about your data management, making sure you're adjusting for the right design features. Okay. All right. So, oh, Willie, question? Yeah. Because you got to speak up. People online can't hear you. Right. So in Stata, if we wanted to, again, create those replicate weights on the fly, I would just say SVY comma BCE jackknife. That changes the default from linearization to jackknife on the fly, like literally when I'm running this analysis. I get rid of this funky if condition. Now if I run that, when you actually run the jackknife variance estimation, look what it's doing. It happened really quick. But see, it showed a dot for each of the replicates that was being created in the background, each of the point estimates and so forth. Now I get a jackknife standard error in addition to my point estimate. And not adjusted for non-response or post-stratification, but still using the same replication approach.
About the number of replicates.
Yep.
Why is it 9 and it was at 31, I think?
The default JKN is always going to base the variance estimation on removing each cluster one at a time. So there were 31 clusters in the data set. There are hence 31 replicates. It's overkill, right? Because there's only 17 degrees of freedom. So there's actually an option in Stata to use only 17 replicates, but the default is to use all 31.
I can change this number of it.
You can't, yeah, you can't change the number created, but you can change which set of replicates to use for the variance estimation. In my experience, it's not going to make a huge difference which of those options you choose. It just could computationally. So here it didn't matter. But if we were using 31 replicates on, say, a structural equation model or something that takes a half an hour to converge for each replicate, yeah, then I'll probably want to use 17. But yeah, the basic JKN technique, one replicate per cluster. Any other questions? Okay, I think we're all set for today then. So next week, we're going to get more into descriptive estimation, including quantiles, medians, other percentiles, functions of estimates, subpopulation estimation, and then we're going to get into categorical data analysis, like chi-square tests and things of that nature. Okay, so that'll be our focus next week. Okay, if anybody has questions about any of the homework that's due on Monday, please make sure to shoot me an email. If you need to meet or anything else like that, you can email us directly. But please make sure to shoot me an email. And just as a general point, always include Young Chow on questions about homework or assignments or whatever, because if I'm in meetings or I'm busy or something, he might see that before I do, and he can respond to you more quickly potentially. So just always include Young Chow on email questions. Okay. All right, everybody have a good weekend, and we will see you on Monday.
Quick question, actually.
Okay, Sarah, yep.
Yeah, according to the syllabus, the one page or the paragraph summary of our project is also due Monday. Do you want us to shoot that just to you guys, or?
Yeah, that would just come by email to us directly. Yep.
Okay, thank you. I just want to make
I'll
sure
say
to
more
do
about
that
that on Monday.
Oh, is it not due before class Monday, or is it?
I'm sorry, Sarah. I'm having a really hard time hearing you right now, but I'll post an announcement about that as a reminder. Yep.
Okay, thanks. Bye.
Okay, thanks.
I did this before. If I feel I bring the data, I wait. You can't have the data.
Can you go back to when you tried to load the data?
I use it. Library table and hands. I copy it from here. Just a second. Data. Yes. Just a minute.
I think it's kind of.
I feel that I brought it to because I don't know.
Then I just copy this.
It looks like you read in the data. So
I have I read the data. Even I have here. I read it.
My father is my father.
okay, but remember, mutate's not its own function. It's part of the operation. So did you load the libraries? Even all of these? Did you load all of these? So if you run this entire thing, it's because it's saying that it's not recognizing the pipe operator. So yeah, so you have it. So maybe just get rid of that comment. Because I think what's happening is the way you've read this in, the file itself, like it's thinking this is code expression into the next function call. Notice how it's not filtered. It's not reading that as a comment. So it's saying pipe operator expression has no idea what expression is. That's not part of that same comment. So just get rid of that, get rid of the comment, 'cause it was read in a strange fashion here. Just delete that comment and run the whole NHANES combination, including. Now run the whole thing, including. Just get done.
If I want big one, it's gonna be $8.
I think it was the issue with the comment.
Oh.
Yeah, comments in the way you have it set
When
up
it's
here.
working for you, when
In comments, they should always be purple.
oh, yeah, I should, I should.
Anything that's not purple is gonna get interpreted as our code.
I got the one with the most.
Yeah, for that, you can just use the confidence level overlap, because we're not there yet. Yeah, just compare the confidence intervals. That'd be fine. Yep. Okay, folks, we have to leave the room. I gotta lock the room, so.
I would like to ask you a question related to publication. I know that my knowledge is very low compared to you, nothing, but I would like to be in your research team or to publish a paper with you.
Okay.
Is it possible?
Yeah. We like I said earlier, we can chat about that like outside of the class. So you can email me about that. We can talk about it further. So I just, if I'm joining papers, I want to read them in detail. I want to understand the design, all that kind of stuff. So let's just talk about that outside of class. And we can figure out how to do it.
So I can send you an email.
Just email me. Always.
For a paper or for a.
Well, just email me we can maybe set up a meeting to talk further about it, like outside of class. But just send me a note and we can set up a time to chat about it outside of class.
Okay.
Yep.
Thank you.
Yep.